Hello everyone, welcome to my YouTube channel. Today I am going to discuss kinetic theory of gas. This chapter is very important for JEE and NEET aspirants, also for the class 11 physics students. Join my Telegram group Physics Prodip to get PDF of class notes and updates. The link of the Telegram group is given in the description of this video. If you found this helpful, don't hesitate to like, share and subscribe to my channel for more informative content. Basically, kinetic theory is a model that explains how gas molecules behave and interact with each other and their surroundings. Kinetic theory relates the macroscopically observed behavior with the microscopic theory based on the atoms and molecules. In kinetic theory, a gas is assumed to consist of a very large number of molecules that move about randomly and collide frequently. On applying Newton's law of motion in a statistical manner to a collision of the molecules, one can relate the average values of certain quantities at macroscopic level. Also, kinetic theory provides the concept of kinetic interpretation of temperature. Now, the basic assumptions of the kinetic theory. First of all, a gas consists of a large number of molecules. Molecules are considered as spherical, rigid and perfectly elastic point masses. The average separation between molecules is large compared with their dimension. I mean, size of the gas particle is very small with compared to the volume of the container of the gas. Molecules of a gas are identical in all respects but differ from the molecules of the other gases in terms of their size and mass. Gas molecules obey Newton's law of motion. So remember it, gas molecule also follows the Newton's law of motion, but as a whole they move randomly within the container with all possible velocities ranging from 0 to infinity in all possible directions. During random motion of the gas molecules, they undergo perfectly elastic collision. So remember it, they undergoes perfectly elastic collisions, okay, with each other and with the wall of the container. Thus, in perfectly elastic collision, both kinetic energy and momentum are constant. So during the interaction of the gas molecules, their kinetic energy and momentum are constant. The forces between molecules are negligible except during a collision. The force between molecules are short range, so the molecules interact with each other only during collisions. Collisions are essentially instantaneous, that is, the time during which a collision takes place is negligible as compared to the time interval between two successive collisions. Also, between two successive collisions, a molecule moves in a straight line with uniform velocity in accordance with the Newton's first law of motion. The distance covered between two successive collisions is called the free path of the molecule. And the last one, in the steady state, the molecular density in any volume of the gas is not affected by the number of collisions. So these are the basic assumptions of the kinetic theory of gas, and remember it, they are very important points. Also, some important points: a gas which obeys all the assumptions of kinetic theory is called an ideal gas, and potential energy of the ideal gas is 0. Also, real gases does not obey the basic assumptions of the kinetic theory. Now, the equation of state of an ideal gas, the equation that interrelates the thermodynamic variables such as pressure, temperature, and density, etc., of a given mass of a gas is called the equation of state. The equation of state for an ideal gas is PV equals to nRT, which is a very well-known equation, where P is the pressure, V is the volume, N is the number of moles, R is the universal gas constant, and T is the temperature. A gas that obeys this relation is called an ideal gas, and the equation is known as ideal gas law. According to this equation, at constant temperature, then pressure is inversely proportional to volume. That is, if we increase pressure, then volume will be decreases. At constant pressure, that is, if we fixed pressure, volume will be proportional to temperature. Also, if we fixed volume, then pressure will be proportional to temperature. So remember these points, these are very important. Also, pressure of an ideal gas inside a container, that is P equals to 1 upon 3 mn divided by V into V RMS square. Now, equivalent form of the ideal gas law. Here are different equivalent forms. One says that PV equals to m by capital M into RT. Here small m is the mass of the gas and capital M is the molar mass of the gas, and small m upon capital M is represents the number of moles of the gas. Another important form, P equals to rho by m into RT. Remember it, rho equals to small m upon V, that is density of the gas, V is the volume of the gas, and PV equals to NKT, where capital N is the number of molecules of the gas and Na is the Avogadro number and K is the Boltzmann's constant. Boltzmann's constant is given by universal gas constant divided by Avogadro number. And fourth equivalent form, P equals to N naught KT, where N naught equals to N by V, number of molecules per unit volume of the gas. Now the ideal gas equation for real gas. So real gas does not obey the ideal gas equation, but real gases obey the ideal gas equation at very low pressure and high temperature. And here is a quantity, it is defined as the compressibility factor, that is Z equals to nRT by PV. So remember this term, this is a another important term, compressibility factor. If we plot Z versus pressure P for different temperature, at higher temperature gases are obeys the ideal gas equation, as dotted line represents the ideal gas equation, and these are the variation of Z with P. Here is this graph represents the variation of Z, that is compressibility factor for with pressure, the variation of Z for hydrogen, for the gas hydrogen into CH4 CO2, and for ideal gas it is straight line which is parallel to the pressure axis. So these are the variation of compressibility factors with pressure. So remember these graphs also. Some physical significance of some constant, that is universal gas constant. Universal gas constant R equals to PV by NT from the equation PV equals to nRT. So R equals to PV by NT, that is pressure into volume divided by number of moles into temperature. And if we reduce the dimension of universal gas constant, then it will be m L to the power 2 T to the power minus 2 and theta to the power minus 1, where theta is the temperature. So R represents the energy per mole per Kelvin, and also it represents the work done by the gas or on the gas per mole per Kelvin, and the values will be 8.3431 joule per mole per Kelvin, also 8.314 into 10 to the power 7 R mole inverse Kelvin inverse, and in general its value is 1.987 calorie mole inverse Kelvin inverse. Also it has a value in liter atmosphere mole inverse Kelvin inverse, that is 0.0821 liter atmosphere mole inverse Kelvin inverse. Another important constant, that is Boltzmann's constant. Boltzmann's constant is given by R upon Na. N is the Avogadro number, the dimension of universal gas constant, and its value is 1.38 into 10 to the power minus 23 joule per Kelvin. Here is another significant constant, that is specific gas constant, represented by small r, and it is denoted by capital R divided by m, that is universal gas constant upon molar mass of the gas, and the values of R is not same for different gases because m is different for different gases. So remember this. Different speed of gas molecules and kinetic interpretation of temperature. If there is a n1, n2, n3, n4 number of molecules and they have speed c1, c2, c3, etc. respectively, then average speed is given by C average equals to n1 c1, n2 c2 plus n3 c3 divided by total number of molecules, that is n1 plus n2 plus n3 dot dot, and mean square speed is given by n1 into c1 square plus n2 into c2 square divided by n1 plus n2. RMS speed, that is root mean square speed, is equal to square root of mean square speed, that is square root of n1 c1 square into c2 square divided by n1 plus n2. And from kinetic theory of gas, the expression for average speed is 8p divided by pi rho. 8p divided by pi rho, also it is given by 8 kt by pi m, and also given this expression is given as 8 rt by pi m, and root upon 8 by pi is 1.6. so the average value or average speed of the molecules is given by 1.6 root over 8 root over rt by capital M, where rho, m, k and t. Rho is the density, m is mass of a single molecule, k is Boltzmann's constant, t is absolute temperature, and capital M is mass of 1 mole of a gas. And c is the RMS speed. RMS speed is given by root over 3p divided by rho, and it is also given by 3 kt by small m, and which is equal to 3 root over 3 rt by capital M. Small m is the mass of a single molecule and capital M is the mass of 1 mole of the gas, and root over 3 is 1.73. so value of RMS speed is 1.73 into root over RT by M. So remember these values, these are very important. Here is some important points. First point says that the RMS speed is greater than the average speed. Also, RMS speed is practically more important than the average speed. Point 2 says that RMS speed is proportional to 1 upon root over rho, that is RMS speed is inversely proportional to the square root of density of the gas, and RMS speed is directly proportional to the square root of the temperature. So at same temperature T, lighter molecules have greater RMS speed as lighter molecules has lower density. Also, kinetic energy of 1 mole of gas is proportional to temperature, as E is directly proportional to 3 upon 2 into RT. So R is a constant, so kinetic energy of 1 mole of gas is directly proportional to temperature. So at different gases at same temperature have same kinetic energy per mole, and mean kinetic energy also directly proportional to temperature. At same temperature, mean kinetic energy per molecule will of all gases is same irrespective of their nature. So remember this point. At same temperature, mean kinetic energy per molecule of all gases is same irrespective of their nature. Also at absolute temperature means at 0 Kelvin, RMS speed, kinetic energy and mean kinetic energy will be 0. So these are the kinetic interpretations of the temperature. So first of all, RMS velocity is directly proportional to root over T. T is the temperature. Kinetic energy is directly proportional to temperature. Mean kinetic energy is also proportional to temperature. And at absolute 0 temperature, RMS speed, total kinetic energy, mean kinetic energy all at 0. Here is another point, that is pressure. Pressure P equals to 1 upon 3 m by V into C square. Then PV equals to 2 by 3 into half mc square, that is twice E by 3. So there is a relation between pressure, total kinetic energy. So P is equals to, and so here P is equals to 2 upon 3 into E, where P is the pressure of the gas and E is the kinetic energy of the gas. This is a very important relation. It gives the relation between pressure and kinetic energy of the gas. Also remember this point, this is a very important point. RMS speed of gas molecule is square root of 3 by gamma times that of speed of the sound. So this relation relates the velocity of sound and velocity of gas molecules. Obviously the velocity of sound in the gaseous medium, as the velocity of sound is given by Vs equals to gamma root over gamma RT by capital M. So this is also a very important relation where gamma is the specific heat ratio, that is gamma equals to Cp by Cv. Now the gas laws from the kinetic theory of gas. First of all, Boyle's law says that if temperature and mass of the gas is constant, P into V gives a constant value, that is P V equals to constant. And Charles' law says that at constant pressure for a given mass, volume is proportional to temperature. So it is a expression for Charles' law. Volume is proportional to temperature. Now Gay-Lussac's law says that for a given mass of a gas at constant volume, if mass and volume is constant, then pressure is proportional to temperature. Avogadro hypothesis says that for equal volume of two gases at same temperature and pressure, then they have equal number of gas particles, that is N1 equals to N2. So here is a proof how to deduce it. And another one is ideal gas law. Ideal gas law says that PV is proportional to temperature, and if we take a proportionality constant, then this relation will be PV equals to RT. So where R is the universal gas constant, so this equation is known as ideal gas equation for 1 mole of gas. For n mole of gas, this equation becomes PV equals to nRT, as already I discussed. Dalton laws of partial pressure. In case of gas mixture, some volume of gases are mixed and they have no molecular interactions, then total pressure P will be sum of the pressure due to all such molecules, that is P is equals to P1 plus P2 plus P3. Graham's law of diffusion. In a gas mixture, two gas of same volume are allowed to diffuse, then C1 by C2, that is the RMS ratio of RMS speed is equal to square root of rho 2 divided by rho 1. So C1, basically velocity is inversely proportional to the density, as I already discussed. Now some graphical representation of gas law. First of all, here is a Boyle's law. As Boyle's law says that at constant temperature, P is inversely proportional to volume. So if we plot P versus that is pressure versus volume, then these graphs like this. For P directly PV, graph is hyperbolic, and also V versus P will be same. And if we plot P versus 1 by V, it is a straight line, that is with a slope of 45 degree with 1 by V axis. Or if plot 1 by V versus P, then also a straight line passing through the origin. Another graph, if we plot PV versus pressure graph, that is the graph will be parallel to the pressure axis. And if we plot PV versus volume, then graph will be parallel to the volume axis. Another graph represents Charles' law. Here Charles' law says that V is proportional to temperature. So the graph will be straight line, but if we take temperature in degree Celsius scale, then there is a extrapolation where graph cut with the temperature axis. But if we take the temperature scale in Kelvin, then graph will be like this. Okay. Another one is Gay-Lussac's law. Gay-Lussac's law says that pressure is proportional to temperature. Plot is a straight line and passing through the origin with a slope of 45 degree. Now these are the graphs represents the Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law. Figure A represents the Boyle's law for different temperatures. So if we increase the temperature, then graph will be like this, where PV equals to constant for Boyle's law. And Charles' law, if we increase pressure, then graph will be like this. Slope of the graph will be decreases. And for Gay-Lussac's law, if we increase the volume, then also slope decreases. And for Avogadro laws, volume equals to constant into n. So it is a straight line if we plot volume versus number of moles in the gas, so it is a straight line passing through the origin. So these are the graphical representation, and these are very important for your competitive exams. So practice them and remember these graphs. Now the Maxwell speed distribution function and most probable speed. Maxwell speed distribution function represents the number of molecules as a function of speed. So NC, if NC is the number of molecules in the gas with velocity c, then it is given by 4 pi n into m upon 2 pi kt whole to the power 3 by 2 c square e to the power m minus mc square by 2 kt into delta c. And the graphical representation graph represents the number of gas molecules, that is NC, with the speed of the gas molecules. Here the CMP represents the most probable speed, and C bar represents the average speed, and C RMS is the RMS speed. So the plot will be like this, and at any point the area under this curve represents the number of molecules. So also, if we increase the temperature of the system, then the plot will be shifted towards right, towards the higher molecular speed, and the plot will be flattened. Here is some important point: at any temperature, the speed of gas molecules vary from 0 to infinity. The area under the curve between any two points gives the total number of molecules having speed between two values. The total area under the curve is a measure of total number of molecules of the gas. The fraction of molecules having either very low speeds or very high speed are very small. As the area in this region is very small, so the number of gas molecules with higher speed, very high speed, and very low speed is very small. Also, the maximum fraction of molecules will process a particular speed, that is CMP. CMP means most probable speed. So the most probable speed is the speed processed by the maximum number of molecules at a given temperature T. At most probable speed CMP, the Maxwell speed distribution curve reaches a peak. So at the peak point, the CMP, that is most probable velocity of the gas molecules, is given by root upon 2 kt by m. So it is also given by root upon 2 RT by m. Root 2 is the value gives 1.41, so its value is 1.41 into root over RT by m. If we compare average speed, RMS speed, most probable speed, then the RMS speed, value of RMS speed is greater. After that, the most average speed, and after that the most probable speed. So if we check the ratio, then their ratio would be C RMS is to C average is to C most probable, then it will be 1.73 into 1.6 is to 1.41. So remember these values, very important for your exam. Now the degrees of freedom. Most important part of this chapter is the degrees of freedom. The degrees of freedom of a dynamical system are defined as the total number of independent coordinates or independent quantities required to specify the position and configuration of the system completely. So degrees of freedom basically for a dynamical system can also be defined as the number of independent motions which the particle can undergo, or the total number of independent quadratic variables by which energy of the system is determined. So in simple way, degrees of freedom can be defined as F equals to 3n minus a, where n is the number of particles or number of gas molecules, and a is the number of independent relations between the particles called a constant or restriction. Always remember that total degrees of freedom of a system is sum of translational degrees of freedom, rotational degrees of freedom, and vibrational degrees of freedom. And if we give some amount of energy to a gaseous system, then the energy will be distributed in terms of translational kinetic energy and rotational kinetic energy and vibrational kinetic energy depending upon the temperature. So it is a very important formula, remember it. F is equals to 3n minus A, where n is the number of gas particles or gas molecules and A is the restriction between them, between the gas particles. Here is some examples of degrees of freedom. For a particle move along a straight line, particle has 1 degree of freedom. If particle moves along a plane, then particles has 2 degrees of freedom. And if particle moves in space, space means in 3-dimensional space, particle has 3 degrees of freedom. For a rigid body at temperature, a rigid body will have 6 degrees of freedom, 3 of its translational motion and 3 of for the rotational motion. At higher temperature, a rigid body vibrates about its mean position. Then the rigid body will have additional vibrational degrees of freedom, so along with translation and rotational degrees of freedom. Degrees of freedom of a gas molecules. It is very important. Degrees of freedom of a gas molecules. If we take monoatomic gas, example of monoatomic gas, helium, neon, argon, etc. Then monoatomic gas consists of a single atom. So here n is 1, A equals to 0, as there is no restriction. If we look at the figure, there is single particle and there is no restriction, that is value of A is 0 and F equals to 3. So the monoatomic gas molecules has only 3 degrees of freedom, and these are corresponding to the 3 translational motion along the 3 axes of the coordinate system. And if we give some energy to the monoatomic system, then energy will be distributed equally in all the coordinates, and it will be half mvx square plus half mvy square and half mvz square, where vx, vy, vz are the velocity of the gas particles, monoatomic gas particle along x, y and z axis. Now the diatomic gas, that is example of diatomic gas are hydrogen, oxygen, HCl, etc. Diatomic gas consists basically 2 atoms at a fixed distance apart but joined rigidly by molecular bond like dumbbell. If we look at the figure, then it is a gas particle or atom, it is another atom, and they are connected by a bond. It is like a dumbbell. So for a diatomic gas, n equals to 2, number of particle is 2, and A equals to 1. As there is only one bond, so there is only one restriction, A equals to 1, and degrees of freedom is given by F equals to 5. So at room temperature, diatomic molecule has 3 degrees of freedom for translational motion and 2 degrees of freedom for rotational motion, and the vibrational degrees of freedom of diatomic molecule is 0 at room temperature. Remember these points. And if we give some energy will be distributed in 3 translational degrees of freedom, 2 rotational degrees of freedom at room temperature. Another triatomic gas, for triatomic nonlinear type gas, that is H2O, SO2, atoms are located at the 3 vertices of the of a triangle. So here n is 3 and A is also 3, and degrees of freedom is given by A 3 into 3 minus 6. So a nonlinear triatomic molecule has 3 translational and 3 rotational degrees of freedom at room temperature, and also vibrational degrees of freedom at room temperature is 0. And if we consider a linear triatomic molecule, that is HCN, CH2, CO2, that is carbon dioxide, 3 atoms are arranged linearly, and here n is 3, A is 2, and degrees of freedom will be 7. So a linear triatomic molecule has 3 translational and 2 rotational degrees of freedom and 2 vibrational degrees of freedom. So remember this, the linear triatomic molecule can vibrate at room temperature. It has 2 vibrational degrees of freedom at room temperature. Here is a figure. This is a linear triatomic molecule. Now the possible vibrational degrees of freedom of gas molecules. For monoatomic gas, as we know, monoatomic gas has only 3 degrees of freedom, and possible vibrational degrees of freedom is given by 3n minus degrees of freedom corresponding to translational motion plus degrees of freedom corresponding to rotational motion. So it is 0 for monoatomic gas. For diatomic gas, the vibrational degrees of freedom is given by 3 minus degrees of freedom corresponding to rotational motion plus degrees of freedom corresponding to translational motion, and it is given by 1. So a diatomic gas can have 1 degree vibrational degrees of freedom at higher temperature. And for triatomic nonlinear gas, the vibrational degrees of freedom is 3, and so a triatomic nonlinear gas can represent 3 vibrational degrees of freedom at higher temperature, and a linear triatomic molecule can have 4 vibrational degrees of freedom at higher temperature. This table represents different gas molecules and number of atoms and total degrees of freedom and their modes. Modes means translational or rotational or vibrational. So monoatomic gas has only 3 translational modes. Diatomic gas has 3 translational modes, 2 rotational modes and 1 vibrational modes. Modes means the transition of energy. If we give some energy, how the molecule behaves or how the energy will be distributed in different parts. So in case of triatomic nonlinear gas, it has total 9 degrees of freedom, and the degrees of freedom will be distributed like this: 3 translational, 3 for rotational and 3 for vibrational. Triatomic linear also has 3 number of atoms, 3, and total degrees of freedom is 9, and it has 3 translational degrees of freedom, 2 rotational degrees of freedom and 4 vibrational degrees of freedom. So remember this table, is very important. Also some important points for any arbitrary gas like ammonia, NH3. As NH3 has 4 atoms, 1 nitrogen or 3 hydrogen atoms, so it has 4 atoms, total 4 atoms. So it has a total 12 number of degrees of freedom, but at room temperature vibrational degrees of freedom are inactive. So at room temperature it shows 6 degrees of freedom. At room temperature degrees of freedom of a diatomic molecule is 5 because vibrational motion does not contribute in the degrees of freedom. At room temperature triad nonlinear molecule possesses 3 degrees of freedom of rotation in addition of 3 degrees of freedom of translation. Triatomic nonlinear molecule has 6 degrees of freedom at room temperature, and triatomic molecule has 9 degrees of freedom at higher temperature. Triatomic linear molecules behaves like diatomic molecule with 3 degrees of freedom of translation and 2 degrees of freedom of rotation. So it has 5 degrees of freedom at room temperature. At higher temperature total 4 vibrational degrees of freedom, hence it shows a total of 9 degrees of freedom at higher temperature. The temperature corresponding to first excited vibrational state of HCl. For HCl is a diatomic molecule. HCl is very high, that is 4156 Kelvin. So for temperature as well below this value, the vibrational degrees of freedom of HCl molecule will be frozen out, that is vibrational degrees of freedom is 0. They will contain little energy and will not contribute to the thermal energy or heat capacity of HCl gas. Also carbon dioxide molecule can indeed vibrate at room temperature, that is 25 degrees Celsius. So carbon dioxide molecules vibrate even when they are not excited by the infrared light or they are not excited. Now the law of equipartition of energy for a dynamical system in thermal equilibrium at absolute temperature T, total energy is distributed equally among all its independent degrees of freedom, and the energy per molecule per degrees of freedom is half kT. So remember this value, it is half kT. The energy distributed per degrees of freedom per molecule, where K is the Boltzmann's constant. Here is some example. If a system has F independent degrees of freedom, average energy of the molecule is half F kT. Total energy associated with n molecules is energy with each molecule multiplied by the number of molecules, that is half F n kT. Energy of 1 mole of gas is half F RT. Total energy associated with n moles, that is half F n RT. And total energy associated with 1 gram, half F R small r capital T. And total energy associated with m gram of gas is half m r m small r capital T, where r is the small r is the specific gas constant. Now here is another table. For monoatomic gas, the average energy is 3 upon 2 RT, diatomic 5 upon 2 RT, triatomic nonlinear it is 3 RT, and triatomic linear gas it is 7 upon 2 RT. Now the specific heat capacity. Specific heat capacity is defined as the heat required per unit mass of a gas, as the internal potential energy of a gas is 0. So the internal energy of a gas was entirely is represented by the kinetic energy of the gas molecules. So internal energy of gas molecules is given by half FRT, where F is the degrees of freedom, R is the universal gas constant, and T is the temperature. Now the smaller specific heat at constant volume, if we define the smaller specific heat Cv by Cv, so molar specific heat Cv equals to du dt at constant volume. So if we differentiate the internal energy of the gas with respect to temperature at constant volume, then it will gives the molar specific heat at constant volume, and the molar specific heat at constant volume is given by 1 upon 2 Fr, where F is the degrees of freedom. And another important relation, that is Mayer's formula. It gives the relation between Cp and Cv, and for a gas, ideal gas, Cp minus Cv is R for n mole of ideal gas. Molar specific heat at constant pressure given by Cp equals to Cv plus R, that is Cv already has a value of 1 upon 2 Fr, so 1 half Fr plus capital R, so it is R into half F or F by 2 plus 1. Ratio of specific heat, that is represented by gamma equals to Cp by Cv. So here is an important relation, gamma is equals to 1 plus 2 upon F. So it is a very important relation, gamma equals to 1 upon 1 plus 2 upon F. Molar specific heat capacity for a polytropic process, that is Pv to the power x, Pv to the power x, then C is equal to R by gamma minus 1 plus R by 1 minus x. Already we have a relation that Cv equals to R by gamma minus 1, so C is equal to Cv plus R by 1 minus x. Remember these relations. Here is two important points. Cp and Cv increase with increase of degrees of freedom of a gas molecule, I mean with the increase of number of atoms in a molecule, and also gamma, that is specific heat ratio gamma decreases with increase in degrees of freedom. Ratio of molar specific heat capacity, here is table. This table represents the molar specific heat ratio of molar specific heat Cp, Cv and Cv, that is gamma equals to Cp by Cv, that is equals to 1 plus 2 by F. For monoatomic gas, its value is 1.67, diatomic 1.4. For triatomic, the value of gamma is 1.29, and for triatomic nonlinear, its value is 1.33. All these values are calculated for room temperature, and also vibration motion is neglected except for triatomic linear gas. Now the mixture of gas molecules, that if two non-reactive ideal gases are mixed, if we consider the first gas, here is a first gas, that it has a mass m1, number of mole n1, f1 is the degrees of freedom gamma 1, etc. And for second gas, these are the variables for the second gas, and after mixing they have values of mass m, number of moles n, f is the total degrees of freedom, and gamma is the specific heat ratio, Cp Cv are specific heat at constant volume and pressure, T is the temperature, is the total number of gas molecules, is the internal and total internal energy. Then these values will be like this. In mixture, total number of moles U will be equal to n1 plus n2, U for mixture, U is equal to u1 plus u2, M for mixture, that is n1 m1 plus n2 m2 divided by n1 plus n2, F, that is degrees of freedom of the mixed gases, that is F mix equals to n1 f1 plus n2 f2 divided by n1 plus n2, and gamma for mixture in terms of degrees of freedom, n is equal to n1 into 2 plus f1 plus n2 into 2 plus f2 divided by n1 plus f1 plus n2 f2. This relation also can be given by N1 plus N2 upon gamma mix minus 1 is equal to N1 divided by gamma 1 minus 1 plus N2 divided by gamma 2 minus 2. Also there is Cb mixed gases, that is Cb mixed equals to N1 Cb1 plus N2 Cb2 divided by N1 plus N2. Cp for mixed equals to N1 Cp1 plus N2 Cp2 divided by N1 plus N2. Gamma for mixed equals to Cp of mixed gases divided by Cb of mixture. So N1 Cp1 plus N2 Cp2 divided by N1 Cb1 plus N2 Cb2, and temperature of the mixed gases, that is N1 F1 T1 plus N2 F2 T2 divided by N1 F1 plus N2 F2. So remember these relations, these are very important for your competitive exams. Now the Brownian motion. Brownian motion, the continuous, perpetual, spontaneous, random and irregular zigzag chaotic motion of minute particle. Minute particle means gas particles of diameter 10 to the power minus 5 to 10 to the power minus 8 meter suspended in a fluid, liquid or gas caused by the bombardment of the molecules of the fluid is called Brownian motion. Here is a representation of Brownian motion. This motion represents the Brownian motion of the gas particles. Okay. So here is specific characteristics of Brownian motion. The motion is continuous, spontaneous, perpetual, irregular, random. No two particles, remember it, no two particles in close vicinity are found to execute the same motion. This motion is independent of the chemical nature of the suspended particle. In same temperature, particles of same weight and size are equally agitated. The smaller the particle size, the smaller the particle size is the greater is the motion. Smaller motion becomes more vigorous on increasing the temperature. I mean, if we increase the temperature, then motion will be vigorous. Lower of viscosity of the fluid, greater is the motion. Hence, the motion is more pronounced in gas than in liquid. And motion is not affected by the shaking of the container. Important characteristics of Brownian motion. Remember these points. Also, here is some important points. Brownian motion is a direct proof of existence of the molecular motion. Large particle size cannot show the Brownian motion. A piece of paper or leaf floating in water does not exhibit Brownian motion. Remember these points. First satisfactory theory of Brownian motion was made by Sir Albert Einstein in 1905 on the basis of kinetic theory, and Jane Perrin experimentally verified the Einstein theory of Brownian motion. Now the mean free path, the straight line path traversed by a molecule between two successive collisions is called a free path, and the average line distance traversed by a molecule between two successive collisions is called the mean free path, that is represented by lambda of the molecule. Lambda is equal to lambda 1 plus lambda 2 plus up to lambda n divided by total number of molecules. Here is an expression from Maxwell. This expression for mean free path is represented as lambda equals to 1 upon root over 2 pi n into sigma square, which is given by m upon root over root 2 pi rho sigma square, where n is the number of molecules per unit volume, sigma is molecular diameter, rho equals to m into n, rho is the density of the gas, m is mass of a single molecule. And mean free path in terms of temperature and pressure, we can use the relation P equals to nkt, then lambda will be equals to kt upon root 2 pi p sigma square. So remember these forms. Coefficient of volume expansion. Coefficient of volume expansion is represented by beta, and beta is given by del V upon V divided by delta, where V is the initial volume of the gas and delta V is the change in volume and delta T is the change in temperature. Here is specific application of coefficient of volume expansion, that is in case of thermometer and thermoregulation. Understanding how gases expand with temperature changes is fundamental in the region of design and calibration of the thermometer used in everyday life and in research also. Gas storage and transportation. Knowledge of the volume expansion coefficient ensures the safe storage and transport of gas in the container, as it helps to calculate volume change under different environmental conditions. Also, climate and atmospheric studies. In meteorology and climatology, volume expansion coefficient is crucial in analyzing the impact of temperature change on the atmospheric condition and climate. Now, another important modulus for the gas, that is bulk modulus. Bulk modulus of a gas is defined as K equals to P upon delta P upon delta V by V, where delta P and delta V are the change in pressure and volume of the ideal gas, and V is the initial volume of the gas. For isothermal bulk modulus of an ideal gas, at constant temperature, PV equals to constant. So if we differentiate it and arrange like this, del V upon V equals to minus del P upon P. So KT will equals to capital P. So in case of isothermal bulk modulus for an ideal gas equal to pressure. Now the limitations of ideal gas law and the van der Waals gas equations of state. An ideal gas equation, that is PV equals to RT, is obeyed by real gas only at high temperature and low pressure, as I already discussed it. At other conditions, there occurs significant deviation from the ideal gas law. So real gases does not obey the ideal gas laws and other conditions. The deviation from ideal behavior are due to the volume of the molecule is negligible in comparison to the total volume of the gas, and there are no force of attraction between molecules. But in practice, none of these assumptions hold good for real gas. So remember this, these two reasons are for the deviation of real gas from the ideal behavior. Now the van der Waals equation of state. So van der Waals introduced two correction terms to the ideal gas equation to obtain the corresponding equation of state for the real gases. First correction was correction for the finite size. The effective volume in which molecule moves is less than the total volume capital V by a factor of V. V is called the co-volume or volume correction term. Remember it, it is called volume co-volume or volume correction term. So V ideal, here V ideal becomes V minus V. Another correction term is the correction for the intermolecular forces. There are forces of attraction between the molecules of a real gas. A molecule within a gas is acted upon by force in all direction by other molecules. I mean, a gas molecules while inside the container, so the pressure on the gas molecules from all direction are equal, but a molecule near the wall of the container, like this figure, if a molecule is near the container of the wall, will experience a inward pull due to unbalanced molecular forces. So here P ideal minus Pi equals to P, where Pi is called the intrinsic pressure arising due to the interaction among the molecules. So Pi equals to A by V square, and the then P ideal, pressure of ideal gas, will be equals to P plus A by V square. So the equation of state of an real gas is represented by P plus A by V square and V minus B equals to RT. And also we can write this relation for an real gas of n moles, P plus A n square by V square into V minus NV equals to nRT. So thank you for observing this tutorial, and if you have any questions or queries, feel free to ask me on the comment section. Thank you for watching.